Všechno dovolený, jak on takhle máme.
Tak přivítám našeho dnešního řečníka. I would like to welcome our today's speaker, Ondřej Guth. He will talk about Automata Approach to Inexact tree pattern matching using 1 degree at a distance.
Thank you for the introduction. Actually, this contribution was presented at Prague Stringology conference this year. What we did, we did a new solution of the problem of pattern matching with trees. It is approximate pattern matching. We propose 3 solutions, 2 based on automata and 3 based on dynamic programming. The problem is quite old. It was firstly presented in 70s by Selkov. So the edit distance is so-called Selkov distance. It works with trees.
Could you please hide the information about sharing the window?
Yes, gladly.
Yeah.
So we have trees. We consider trees as rooted trees, oriented trees, labeled trees, where we consider node labels and we ignore edge labels. And the trees are also ordered in the sense that that the children order of the children is important. So over these trees, we consider Selkov distance or 1 degree edit distance, where we consider operations relabel of vertex. So any vertex can be relabeled, anything there. Then we consider 2 leaf operations. One is leaf insert. So we can insert a new node only as a leaf. So, for instance, we can insert a new leaf under A anywhere, but it must be a leaf. Or and we can do it recursively. So we can insert 2 leaves, like leaf under B and then leaf under the new leaf. So this is also possible. And similarly, leaf delete. So we can delete any leaf. There's one exception: we cannot delete root. So root must always stay there. And again, this could be done recursively. So we can delete C, then A becomes leaf, so it can be deleted after that. For the distance, we always count the operations. We use simplified version of the problem, which is unit cost. So every operation costs 1, but it can simply be extended to with penalty metrics to any cost. So that was the old problem from the 70s. What we did was extension of this problem to pattern matching. Pattern matching is also quite an old problem, maybe older than the distance. What we did, what was novel, was a combination of those 2. So we proposed Inexact 1 degree tree pattern matching problem. The difference from simply computing the distance of 2 trees is that here we consider 1 tree, which we call pattern, that is given in advance. We reprocess it somehow, and then we consider 2nd tree. We call it input tree, which is usually much bigger than the pattern, and we are finding all the subtrees of the input tree, which are isomorphic to the pattern up to some limited number of errors in Selkov distance. So let's consider this left tree as the pattern tree. And then let's consider this right tree as input tree. So then we got some limit of errors. Let's say it's 2 in this example. So we are searching for all the subtrees. By subtree, I mean a tree starting at some node and containing everything from that node down to the leaves. So what can we find here? So if we start in the root, we cannot find occurrence of that pattern, because for that we would need more operations than just 2. Starting from A2, we can find an occurrence, because this subtree is isomorphic to the version of the pattern with the b's deleted. We delete 2 b's, so it's cost 2, and then we can find AAC, and here also AAC. So this is how the problem works. So our approach doesn't really use the 3 algorithms, original 3 algorithms. We help ourselves with knowledge of string pattern matching, and we tried to convert or to view the trees as a string. So we use the so-called prefix bar notation, which is just some encoding of pre-order traversal of the tree. So let's have our pattern tree, and its prefix bar notation is this one. And why? Because we traverse the tree in pre-order. And we can consider the notation, the string notation, as parenthesis notation. So every time we go through a node, well, this is the tree. So every time we go through a node, we open a subtree. Every time we exit from a leaf, we end the subtree. So we note it with the bar or pipe symbol. Which corresponds to closing parenthesis. So basically, we only omit opening parenthesis and we encode only closing parenthesis. So when we go through this tree, we get A, which is the root, then B, which is a leaf. So we end the subtree, then B again. Again, we end the subtree, then we go to the next child, so which is A and C. With C, we close the subtree, which corresponds just to the leaf. Then we close subtree, which corresponds to this A node. And then we close the subtree, which corresponds to the whole tree. So that's why here are 3 bar symbols. So this is how this linear notation works. It's just this simple. Okay, so so the next problem was to encode the 1-degree tree edit distance on strings, which is, I guess, quite straightforward. So basically, again, we have a pattern tree and input tree. So how can we find, for example, this occurrence? How do we compute it? So when we start in this B7 node, we definitely need to rename the root. So it's 1 operation. Then we continue with A and C. So probably the smallest number of the next operations is deleting B2 and deleting B3, which is in total 3 operations. How do we do it on prefix bar notation? On prefix bar notation, we need to be careful about a few properties which work there. One of them is a locality principle. Whenever we work with a subtree, it's always a substring in this notation. So when we start with our pattern, First, what we need is to rename the root to B. So this is intermediate prefix bar notation. Then we need to delete the B2. And when we delete a leaf, it means that we need to delete the label and the corresponding bar symbol, which are always just adjacent. So that's why we get this intermediate notation. Then we delete this B, and again, we just delete the substring B bar, and that's why we get this in the end, which corresponds to this subtree. Similarly, with inserting, because we need to allow recursive inserting, so whenever we insert some label, we also must insert the bar symbol just next to it. That's why this A bar appears here. If we want to insert C, then again C bar appears there. So using this trick, we can encode inserting leaf anywhere, even recursively. So with the prefix bar notation, the problem is formulated again quite similar way. The difference is what we find, because on trees we find always the root of the subtree, which corresponds to the isomorphic image of the pattern up to k edit operations. With prefix bar notation, we can find some substring which corresponds to the occurrence, and the substring can be represented in several ways. It can be represented as an interval of indexes. It can be represented as starting index and length, or ending index and length. We use the latest one, but it doesn't really make much difference. Okay, due to time, I will skip this. I hope it's quite clear what we are doing. So how do we solve it using Automata? The first thing we use is pushdown automaton. Not only because pushdown automaton can be used for many tree-related problems when we encode trees as strings, but we need it here for insert operation. For clarity, I will use always the same tree pattern as an example. And our automaton for that example looks like this. It looks quite messy. I am sorry for it, and I will explain it by parts to make it more clear. So as a base of that solution, we use the string pattern matching automaton, which is known for a few decades. So there is a part of that automaton, of this one, which reads exactly the pattern. So this is all the same for all pattern matching automata in strings. For this, we don't use pushdown operations. So basically, we start at some state and then read the prefix bar notation of that pattern tree. So A, B, bar, etc. And the only final state, the only accepting state there is the state after we read the complete pattern. So this definitely doesn't make it approximate pattern matching, and it also doesn't make it pattern matching at all. We are missing one part, which is the so-called pattern matching loop. So this automaton is non-deterministic, and using it pattern matching loop, it works. It uses that idea that the automaton starts reading the pattern at every position of the input. So this way we don't miss any occurrence. There is one extension to the classical theory of automata and languages. So this automaton doesn't work as ordinary pushdown automaton because ordinary pushdown automaton can only accept or reject the whole input. So in the basic theory, when we read the whole input, and at that time when we finish reading the input, we are at the final state. Then we accept it. Otherwise, we reject it. This automaton works more like a sort of transducer because here we consider finding an occurrence whenever we reach final state. Regardless we read the whole input or not, it doesn't matter here. So this is some sort of simplification or modification of the basic theory, just reaching the final state and we are happy. Also, whenever we reach the final state, we can mark that occurrence in the input as the end position of occurrence of the pattern. Okay, so this part of the automaton can do exact pattern matching without any distance, without any inexact finding. The other states there are for encoding the number of errors or the number of edit operations. There's no other purpose of them. So we can understand the automaton in sort of some floors or layers, where the first layer marked as 0 here is for no edit operation at all. And whenever we need to do some edit operation, we just jump to other floors. So here's the floor for one edit operation. Here's the floor for 2 edit operations. So the states here encode how many operations we did so far, because still the problem is that in advance we have the limit for number of edit operations that are allowed. We are not interested in finding any occurrence with more edit operations than the number. Let's say here it's 2. Okay, there are definitely also many more transitions. So the horizontal transitions always correspond to the symbols that are used at node labels at that position. So when we go horizontally, we just read the pattern without any edit operation. Then there are the relabel operations. So wherever we are, instead of reading a symbol, we can read any other symbol. And because it costs 1, we need to jump to adjacent floor. Note that this relabel operation cannot happen when we read the bar, because we cannot relabel bar. Bar is a special symbol. It's not symbol from the alphabet. It just denotes end of subtree. When we relabel bar, it means we change the arity of that node, which we cannot allow. It's something different. It would mean we can accept something else than Selkov distance. Also, here's an epsilon transition. Epsilon transition, here by epsilon we encode the empty string. And in the theory of automata, it means we can simply use that transition regardless what's on the input. So we can just in non-deterministic way skip from this state to this state anytime we wish. This is used for encoding the delete operation. So just to remind, what does delete mean? Delete means we can delete only a leaf. So we can delete the substring, the symbol, and the bar. Only this substring means delete. So that's why the epsilon transitions always go over symbol and bar, only over this pair. Otherwise, it would again mean something different than Selkov distance. Some of the epsilon transitions are longer, like this one, because this corresponds to deleting C and then A, like recursive deleting of two leaves. So we need to remove the substring A, C, bar, bar. That's why this epsilon transition is longer. So there are things which need to be pre-computed before we start constructing this automaton. Of course, most of the things can be done in or are known simply, but like those long epsilon transitions aren't that simple to compute, and I will cover it just after a while. The last thing, which I hope is somehow interesting, is the insert operation. So again, what does insert mean? Insert means that we can insert any leaf, which means we can insert a substring like leaf symbol or node symbol followed by bar. And again, this can be done recursively. So the substring can be longer, it can be more complicated. And basically, there are two cases. One case is that we are inserting two independent children, like those two B's. So it means we insert B bar, B bar. Or we can insert two nodes when where one each is child to the other, and then it's A, C, bar, bar. So there are more combinations of what we can legally insert. And this is encoded in the vertical transitions. So this, for instance, this transition means we insert a symbol, node symbol, and this loop means we insert the bar symbol. We cannot, because here is a loop, we cannot allow to this to happen unlimited times, because that would lead in that could lead in false positive occurrence, which didn't really happen. Because just to remind, we are reading some longer input and allowing consuming unlimited number of bars could mean that we are finding something which is not occurrence because we are reading some weird part of the tree. We only need to find some subtree which corresponds to the pattern. So this is where pushdown operations come into the game. Because whenever we are attempting to insert some symbol, we remember it on pushdown store with this C pushdown symbol. And whenever we are removing or reading bar symbol, we are removing that C from pushdown store. So there is a principle of pairing. We always need to remember how many nodes we have inserted, and then we need to read exactly the same number of bar symbols because they must always match. Otherwise, it's not inserting of leaf, it's something different. So that's why all the other transitions which are not used for the insert operations require that the pushdown store is empty, or there is only the starting pushdown symbol and nothing else. Because otherwise we are not sure about the balance of input symbols, node symbols, and bars. So this is the whole idea of the pushdown automaton, where I was in a different part, where the pushdown store is used just for inserting. For the rest, it's not so necessary. For computing these long epsilon transitions for deleting a more complicated subtree, we reused the data structure called subtree jump table, which is an array which just maps any position in the prefix bar notation to some other position, where if we are interested in the bar symbol, then the subtree jump table refers us to the left, so basically up in the tree. So for instance, this position 3 corresponds to the end of this subtree, which corresponds to the B node. So the subtree jump table tells us where's the node before that subtree, which is this A. So that's why here's 1. On the other hand, when we refer to the node label, subtree jump table tells us where is the next sibling, or in general the next label after the whole subtree. So if here was some other child of A, then when we take a look at this node, it will lead us to the next sibling. So we skip the whole subtree. So this this data structure can be computed in a linear time, and we use it for skipping the subtrees. So for the delete of pre-computing of the delete operation of the transition for the delete operation. Okay, so when we took a look at this pushdown automaton, which we constructed using some knowledge of Stringology, and also we tried to think of the problem as itself. We noticed that the pushdown store almost isn't needed. Its need is very restricted because it's only needed for the insert operation, and also the number of insert operations is limited in advance. We know in advance how many symbols can be inserted, so we can pre-compute all the possible combinations of symbol and bar. So this can be encoded in states, and we don't need pushdown store at all. Why can we do it? The reason is that algorithms that work over pushdown store automaton are more complicated than algorithms that work for finite automata. For example, it's not easy to create a deterministic version of this automaton. Not that such algorithms don't exist. Not exactly for this type. It needs to be transformed to something else in advance, and then the complexity of that determinization algorithm is really high. It's quite inconvenient. So definitely we can do better work with finite automaton. So the finite automaton is just the same as the pushdown automaton. The only difference is just in encoding of the insert operation. So what's the basic idea of encoding of the insert operation? It is that besides the states, the black states in this notation, which encode just the distance, we also encode all the combinations of the node symbol and the bar. So, for instance, this situation means that we inserted just one node symbol, and now we are waiting for the bar symbol. We can either consume the bar symbol, then we know that that we successfully inserted one node, and we can continue with any other operation, or we can insert one node symbol and then second node symbol. So after that, we know that we are waiting for two bar symbols in order to insert a complete subtree. Or of course, we can insert one node symbol, then bar, and then another node symbol and bar. So this is also possible for two insert operations. Of course, with the number of allowed errors, this will grow when we go to the bigger number of edit operations. So yeah, this is disadvantage of this approach. Still, with pushdown store automaton, nothing like that can happen because we solve everything on the pushdown store. But the non-determinism of the pushdown store isn't also really great value there. Okay, so this is definitely finite automaton. It can be transformed to deterministic finite automaton. And we can use all the algorithms that exist to work with the non-deterministic finite automaton directly. Then we got idea for one of them, so I will present it right away. And I hope the idea behind this automaton is understandable. One of classical solutions for pattern matching or even approximate pattern matching in Stringology, which corresponds some way to an automaton, is a dynamic programming technique, where we can find correspondence between active states of a non-deterministic finite automaton for pattern matching, and the value in some cell when we visualize the dynamic programming using the table. So we reused and extended this classical technique. In this classical technique, we after reading a symbol from the input, we encode which states in the automaton as a whole could be active. And here we have 3 dimensions, which is not usual. Usually, dynamic programming for pattern matching is just 2 dimensions, and I will explain all of them. We can consider encoding of the automaton here in the D table. Like we turn it 90 degrees. So here, vertically, this corresponds to the pattern. So this corresponds to the horizontal dimension in the automaton. The number inside, please just for now ignore the multiple dimensions in each cell. So let's consider just the first value. So the number here corresponds to the depth of the state which is active. No, it's bad, sorry. The row corresponds to the depth of the state. By depth, I mean how much to the right I got in the automaton. And the number corresponds to the distance. So, for example, here, the first row always includes 0, which means this starting state is always active. Why? Because of the pattern matching loop. That's the reason for pattern matching loop. We need the first state to be always active. Then, after I read a symbol from the input, which corresponds to the root, I can reach this state 1. So it corresponds to the first row because of this depth. So any state in this set of states corresponds to some number in the first row. And here is 0 because the state corresponding to the 0 number of edit operations is active. That's why 0. 0 like 0 layer. If I take it from the end, for example, consider state this state 9 in the second layer, in the layer corresponding to 2 edit operations is active. After we read bar symbol, we reach the last row, which corresponds to the accepting state in the layer corresponding to 2 errors. Whenever we reach the final state, we found a recurrence. Each layer corresponds to the number of errors. So we know we found an occurrence with the Selkov distance 2. And so whenever we find any number in the last row, it corresponds to the end position in the input. The basic idea, which I forgot to mention in this dynamic programming approach, is that we transfer the values diagonally. Yeah, so from here to here, or from here to here, which corresponds to simply going in the automaton to the right within the same layer. Okay, the similar thing is for relabeling. So, for instance, from this state, we can read a symbol not which we can't here because there's symbol B in the pattern. So we need to relabel. So we take the original value, which is 0, and add 1 because the cost of relabel is 1. Here, I guess the most complicated action is the delete operation. So I'll try to explain it. In the automaton, the delete operation corresponds to the epsilon transition. So when we try to delete this subtree, which is this node, we just skip the B bar and continue next with the input. We can, of course, delete the two leaves, B and B2 and B3. In the automaton, it means we use the epsilon transition twice, and we deleted both of them. The problem is that in our dynamic programming approach, we don't have any epsilon things. We always need to compute what happens after we read some concrete symbol. We can't read strings, we only read symbols. So what we need to do here is a simulation of what can happen after deleting whatever, or skipping whatever by epsilon transitions, sorry. So that's why in the algorithm there's a loop. So for instance, how do we know what can come here in this cell? Why is there 2? It's because we read a symbol. It's this one, and then we need to take a look what's before it. So before this a symbol, there's a bar, which means it's an end of some previous subtree. So what can we do? We can skip that using subtree jump table. Using subtree jump table, we know how much we can skip to the back. So we skip. And before that subtree, there's another subtree because another bar symbol. So again, we skip it. And before we see there's 0. Because we skipped twice, 2 subtrees of size 1. It's 2 together. So edit distance is 2. That's why 0 plus 2. Similar situation is here. We read the B symbol. We read the A symbol, but here's B. So we definitely need relabel. That's 1. And again, skip of subtree of size 1, which is 2. So 0 plus relabel and delete is 2. That's the principle. The principle is we do something like reverse tracking where epsilon transitions happen and what can happen after them. That's why the formulas are quite unreadable, maybe. And finally, the insertions. The insertions use the additional dimensions in the cells of the D table. So what happens when we start in this state 100? After we read A, we can try to consider it as insertion. So it's distance 1, and we use this middle value to encode, okay, it can be insertion or not, we don't know yet. because we don't know the input which is to the right from us. Okay, we read another A. So well, this red one corresponds to this blue 111. Then we read another A. So it can be nothing else than another insert. So we take this one plus one, which is 2, in the rightmost position in the cell, which means we already read 2 symbols, and now we are waiting for 2 bars. So after we read the bar symbol, okay, and now here is C, which means the third insert, which cannot happen because the limit for insertions is 2. So this wasn't successful insert, we forget it. So this 2 is forgotten. If I track the blue ones, so we go from 0 to 1, then to 2, and then we read the bar symbol, so we can move the 2 to the middle position again. After the next bar symbol, we can move the 2 to the leftmost position. Leftmost position in the cell means the number of symbols and bars is balanced. We inserted complete subtree, and we can go on with any other editing operation or matching operation. So this is the idea how to encode the insertions in the D table. So the D table, or this table which visualizes the dynamic programming, or the idea behind it, comes directly from the automaton. So we can consider it as a simulation of the non-deterministic automaton in some deterministic way. So because I guess you are all familiar with dynamic programming, so I hope you can see that that the space complexity is that for the space complexity or for the computation, we always need only the previous column. So the space complexity corresponds to the size of the column. The size of the column is the length of the pattern times the number of dimensions, which is the limit for the number of errors. The time complexity is we need to compute all the positions in the table, so it's the space complexity times the length of the input. There is some trick. What is tricky here is the delete. In the paper, there is a proof that that the delete doesn't that the computation for the delete, even though there is a loop, it doesn't add to the complexity. The trick is based on the fact that the number of possible jumps in the delete is again limited by the maximum number of errors. So so it's not unlimited. There's the loop, even though the loop is over the size of the pattern, it's limited by k, which is much smaller number, so it doesn't add to the complexity. Okay, that's it for the presentation. And if you have any questions.
So I wanted to ask, what's like, this is the dependence once we have the table ready. So how long does the preprocessing take? Like, what's the dependence on the pattern for the preprocessing phase?
Well, the table isn't constructed from the automaton. It's only based on the same idea, but we don't need the automaton for the table. And so the only thing we need is we need 2 things. One thing we need is the prefix bar notation, which needs just linear time, just pre-order traversal, and also we need the subtree jump table, which also needs only linear time. So the linear time in the size of the pattern.
Thanks.
Thanks. Yes.
I have only maybe a technical question. What do the numbers in the table mean? The number of mistakes which happen?
Yes, the number, the distance in unit cost cell of distance. Yeah. So the number of edit operations.
Okay.
This is for the leftmost dimension. By infinity, you can consider anything higher than the limit. So when the limit is 2, then the infinity could be 3 or whatever which is not in the interval 0 to k.
Yeah, yeah, okay.
And the other dimensions there, it is also the distance, but only intermediate result for insert.
Well, this question of mine stems from the fact that the number of states in the table is n times k squared. But the k squared is somehow encoded in the number of mistakes and the position.
And times.
So because you end up in the same state, whether you have like one additional and bar and one additional and bar, or you have like two additional symbols and two bars. You
Yeah.
end in the same state, right? So
Yeah.
why you didn't have to remember both of these options?
Because for the problem, you don't. I'm not sure if I understand the question correctly, but if I understand it correctly, then for the problem, you don't really care how you got there. You just need to know the number of errors because there is the limit. So that's why we don't do it here. It's just so yeah. Maybe the question goes to another question. If we can track how we got the occurrence, and no, not easily. From the table, we cannot get it. We can, but we need additional computation. We just from the information that is here is true. We don't know here is 2. We don't know. We can easily compute the root of that occurrence because of Subtree jump table, but we don't get easily from all those numbers here which were exactly the operations how we got there. It's not encoded in the table.
Would it cost like too much memory extra to keep track of how we got the values if I wanted to backtrack by which edit operations the match happened?
Well, to be honest, I was thinking of it in a really long past ago, so I don't remember. Maybe here will be. So I can't tell honestly if it's how much it would be. I don't know at the moment.
Okay, there are no questions. Let's thank our speaker again.